Hello everyone, Mehdi Mortazavi here with one example from the Brayton cycle from engineering thermodynamics. So in this example, we have an ideal gas turbine cycle which has two stages of compression and two stages of expansion. The pressure ratio across each stage of the compressor is given at 3, and also we have the same pressure ratio through the turbine. Okay, so these 3 is basically the ratio of the pressure after the compressor versus before the compressor, and also the pressure of the working fluid before turbine versus after turbine. Air enters the compressor at 300 Kelvin, and because we have two compressors and at the inlet of both compressors this is the same temperature, so technically this means we have an intercooler between the two compressors. Also, the working fluid or air enters the turbine at 1200 Kelvin. So once again, that simply means between the two turbines we have a reheat. The question is asking for the back work ratio. So the back work ratio is the ratio of the compressor work to the turbine work. Also, the question is asking for the thermal efficiency, and in part 8 there is no regenerator involved. So what I'm going to do, I'm going to start problem like this by doing the schematic first. Doing the schematic really helps in solving problems. So let's say I have two compressors. Let's say this is my first compressor and this is my second compressor. Let's say air enters into the compressor, and then before the second compressor there is an intercooler. So this IC is my intercooler. After that, air is sent to the combustion chamber. So let's say this is the combustion chamber, and after that air is sent to the turbine, and we have two turbines. Okay, after the first turbine, the working fluid is passing through a reheat, and the reason behind that is because in the problem statement it says the temperature at the inlet of each turbine is 1200 Kelvin. All right, and finally air exhaust to the atmosphere. So let's say this is my compressor number 1, this is my compressor 2. So compressor 1, compressor 2, compressor number 2, turbine 1 and turbine 2. Turbine 1 and turbine 2. Okay, and obviously there is a shaft that connects all these four equipment to each other. So let's say this is my shaft, and also that shaft extends, and there is a rotation in this shaft. So the rotation or the work that these two compressors need is coming from these two turbines. Okay, so also before solving the problem, let me show the heat addition in this process. In this process, the heat addition occurs within the combustion chamber as well as within the reheat. We want to be careful with this reheat because in the reheat we are also burning fuel. So here we have Q in and here we have Q in. In order to find the back work ratio that is asked, I need to find the compressor work as well as the turbine work. Okay, but before jumping into that, I would also like to do the TS diagram for this cycle. So let's say I have a diagram like this. Temperature is the vertical axis, entropy S is the horizontal axis. And what I'm going to do, I am going to show this 8 points that I have in this cycle. Let's say point 1 before the compressor, point 2 after the compressor, 3, 4, 5, 6, 7, and 8. Okay, so I have two temperatures. I have the lowest temperature, which is 300 Kelvin, and the highest temperature, which is 1200 Kelvin. The reason that I say this is the lowest temperature is simply because this is the temperature before the compressor, or let's say point 1 and point 3. And these temperatures should be the highest temperature because they are at the inlet of the turbine. At the inlet of the turbine, we have the highest temperature in the Brayton cycle. So I can show 4 constant temperature lines. So let's say these are my 4 constant temperature lines, and with the help of these 4 horizontal lines, I'm going to show my cycle. So let's start with point 1 or state 1. State 1 is before the first compressor, and from 1 to 2 the temperature increases. But because this is an ideal cycle, then technically S or entropy does not really change. So entropy is the horizontal axis. All right. So this tells me S is constant and S is entropy. We learned that back in thermodynamics 1. So from 1 to 2, S is constant, but the temperature increases. From 2 to 3, the working fluid or air is losing heat to the surrounding. This intercooler is basically absorbing heat from the working fluid and makes it colder before the second compressor. So 2 to 3, the temperature drops, but again from 3 to 4, through that compression, the temperature increases in an S constant process. So far I have these like Z-shape processes so far. From 3 to from 4 to 5, we have the heat addition within the combustion chamber. So the temperature of the air increases significantly. All right. So from 4 to 5, this is what I have. And from 5 to 6, the working fluid is passing through the first turbine. So I have the first stage of expansion from 5 to 6. From 6 to 7, the second stage of heat addition is done. The reason that I say that this is the second stage of heat addition is simply because from 4 to 5, we did the first stage of heat addition. So from 6 to 7, the temperature increases in an S constant process. Like the pressure at point 6 is equal to pressure at point 7 in an ideal cycle. Finally, from 7 to 8, we have the second stage of expansion. So this is my cycle on a TS diagram so far. Okay, so what I will need to find in order to obtain the backwork ratio is, let's say this RBW is the backwork ratio, and that is WC over WT. Okay, but this WC is the work of compressors 1 and 2. Like there are 2 compressors into this WC. This WT, which is the turbine work, includes the turbine 1 and turbine 2 work. Okay, so that means this is going to be equal to WC1 plus WC2, and for turbine work I would say WT1 plus WT2. Okay, WC1 is equal to H2 minus H1. Okay, so this is the first compressor, and the work of the compressor is equal to the difference in enthalpy. WC2 is also equal H4 minus H3. Okay, WT1 is H5 minus H6. And finally, WT2 is H7 minus H8. Okay, now in order to be able to find this backwork ratio, what I need to obtain is bunch of enthalpies. Basically, I need to obtain enthalpies for all 8 points. This is my recommendation to you. I'm going to make a table like this that lists all 8 points. And in this table, what I'm going to find is the enthalpy column. But before that, I have some other properties such as temperature, the relative pressure, and enthalpy at the very end. So my goal is to fill out this column for all 8 points because I need the enthalpies for all 8 points. I need to fill out here. Okay, so let's start with the first point. One thing that I can add on this TS diagram is the temperature here and here, because the lowest temperature is given at 300 Kelvin. So that's what I have here. And also the highest temperature, which is before the turbine, is 1200 Kelvin. And before turbine is includes points 5 and points 7. So that means temperature here is 1200 Kelvin. Okay, so for the first row, my temperature is 300 Kelvin. And based on that, I can go to the table and read the H value. Okay, so you want to use table A17 because the working fluid is air. In table A17 of our textbook, the enthalpy is 300.19. Also, because I'm in the table, I also read the relative pressure. This is PR, or the relative pressure, and it's a dimensionless number. So from the same table, PR is 1.386. All right, now in case you're wondering why did I obtain PR from the table, the reason is I'm going to use this PR to find PR at point or state 2, okay? Because one thing I know is the process from 1 to 2 is a S constant process, so I can develop an equation like this. I can say P1 over P2 is equal to PR1 over PR2, and PR being the relative pressure, and that ratio is equal to the pressure ratio which is given in the problem statement. So the problem statement gives me the pressure ratio of 3. So that means I have the value of this pressure, the value of this, the value of this ratio. The value of this ratio is the pressure ratio which is equal to 3 and is given in the problem statement. Now, this PR1 is exactly what I have here. So this is checked. Based on that, I can find PR2. So that gives me the relative pressure at state 2 equal to 4.158. Okay, so I'm going to add this number into this table, which is 4.158. And based on this PR within the table, I can read the H value. So the H value from table A17 is 411.12. And the temperature, although we don't really need the temperature for state 2, but because we are in the table, we can also read the temperature, which is 410. All right, so if I continue, but before I continue, let me explain one thing. So this equation, you want to be careful with this equation. This is only good for S constant properties. Like you can write the pressure ratios based on the relative pressure ratios as long as your entropy is constant. If your process from 1 to 2 is not an S constant process, you cannot do this equation here. I'm talking about this equation. I'm talking about the equation of the pressure ratios. All right. So this portion is only good for S or entropy constant. Okay. As long as your entropy remains constant, you can do the same thing here. Okay. Now, points 1 and 3 are exactly the same. They are both the inlet of the compressors. This is point 1 and this is point 3. So that means I can just copy this line for line 3. So my temperature is 300 Kelvin, my PR is the same value, and my H is also the same value. Okay? Likewise, points 2 and 4 are the same. They are both states after the compressor. So for state 4, I can say the temperature is 410, which is right here. The relative pressure is 4.158. And my H value is 411.12. Okay, so let me just draw a line here so it is easier to follow all these numbers. Oops. Okay. Okay. Now let's go. So basically at this time we are done with this portion of the cycle. We are done with the compressor portion of the cycle here because we did points 1, 2, 3, and 4. Now we want to do this portion of the cycle which belongs to the turbine. And in case I forgot to include the direction of the cycle, so obviously we go from 4 to 5, from 5 to 6, from 6 to 7, and from 7 to 8. So basically this is the direction of the cycle we are following. Okay, I am going to use the same concept that I had here for process from 5 to 6 because the process from 5 to 6 is another S constant process. So I can easily say P5 over P6 is equal to PR5 over PR6. All right, and that ratio is equal to RP or the pressure ratio. Now, if I get back to the table, for point 5, actually, I can add PR value because I have the temperature for point 5. The temperature for point 5 is 1200 Kelvin, all right? So this is 1200 that I have. And again, from table A17, I can read PR value. And that PR is 238. Because I'm in the table, I can also read H value, which is 1277.79. Okay, and by the way, exactly the same numbers apply to this row because points 5 and 7 are exactly the same. 12, 77.79. Okay, now based on this correlation, I can solve PR6 because I have PR5, I have this pressure ratio which is equal to 3. So that gives me PR6 equal to 79.3. So keep in mind that PR5, I already have it. So this PR5 is 238. And the only unknown that I have is PR6. Now I can add PR6 into the table, 79.3, and I can rate H value based on these PR. Okay, so just for one example to show you how to read H value based on PR. So let's say we have this PR value and I know the working fluid is air. So I will go to table A17. Well, it really depends what textbook you are using. In the textbook that we use, which is basically this one, a very great textbook. The title is Thermodynamics and Engineering Approach. I am using 8th editions, but 7, 8, and 9 are exactly the same. And the author is basically, I'm not sure if you can see, sorry about that. So these two are the author. Sengel and Bowles are the author. Okay, so going to A17, this is my A17 table. The title reads, in case the reflection is not good, the title reads Ideal Gas Properties of Air. Okay, and what I'm trying to do, I'm trying to find my PR value. So let's say for 0.6, our PR was 79.3. So this is all PR values. If you keep continuing, you will see that the PR column is increasing. Now, I will pick up from here. The PR is increasing. Let's say between these two rows, where's my pencil? So 79, I said, right? So 79 is between this number, between 75 and 82. So what you want to do, you want to do some interpolation here, basically. So you want to do the interpolation between these two PR values to find your H value. So basically, by doing the interpolation, I should expect to have an H value greater than 932 and less than 955. Okay, so I've done the interpolation before, and that value is going to be equal to 945. And also, although we don't really need the temperature, but just in case, let me also give you the temperature, which is 916 Kelvin for 0.6. Once again, this row exactly applies to this row. So the temperature is 911, 79.3, and 945 for the enthalpy. Now at this time, we have the enthalpies for all 8 points. This is H1, H2, H3, and so on. So that means I can easily calculate these compressor work as well as the turbine work. So these two give me the compressor work equal to 222.1 kilojoule per kilogram, and also the total turbine work is going to be equal to 665 kilojoule per kilogram. All right, so if I get back into this equation at this time, WC is known, WT is known, and based on that, I can calculate my back work ratio. So the back work ratio is going to be RBW is going to be the compressor work, which is 222.1 kilojoule per kilogram, over the turbine work, which is 665 kilojoule per kilogram. Okay, and that is equal to 0.335. Now, in case you want to report that the back work ratio in percentage, it's going to be 33.5%. So this number simply means in these power plants, almost 1/3 of these compressor work is sent to the, almost 1/3 of the turbine work is sent to the compressors, basically, or 33.5% of the turbine work is sent to the compressors. Maybe I can just write this down here. 33.5% of the turbine work is sent to the compressor. All right. So that is obtaining the backwork ratio in this cycle, but also I need to find the thermal efficiency. But thermal efficiency is in fact very simple, because the thermal efficiency is the ratio of the net work to the heat addition. So the thermal efficiency is equal to W net over Q in, and this W net itself is WT minus WC, turbine work minus the compressor work, and Q in stays. All right, so these two W's are known at this time. The only thing that I need to find is Q in. But if I get back into this schematic, Q in occurs in two stages. In one stage, that Q in is the difference in enthalpies between points 5 and 4. And in other stage, my Q in is H7 minus H6. So if I want to develop Q in, maybe I can do it here. So my Q in is H5 minus H4, that's stage 1, plus H7 minus H6. Okay, so the first stage occurs within the combustion chamber, and the second stage occurs within the reheat. Okay, so if you do the math, you will end up with Q in equal to 1197 kilojoule per kilogram. So this is what I would need to obtain the thermal efficiency. So this is 1197 kilojoule per kilogram. And for WT, for turbine work, I had 665. And for the compressor work, I had 222.1 kilojoule per kilogram. All right, so compressor work minus the turbine work over Q in. And that gives me a thermal efficiency of 36.8%. So I multiplied by 100% to obtain this value. So that is my thermal efficiency in this cycle. All right. Okay, now that we are done with part A, let's do part B of the problem. In part B, we also need to find the backwork ratio and the thermal efficiency of the cycle, but this time in part B there is a regenerator, okay? And the regenerator has a specific effectiveness which is 75%, right? So what I'm going to do, I'm going to do part B similar to part A. In fact, the schematic looks pretty much the same. The only difference in part B is we are going to have a regenerator, okay? So let's do that. So I will start with the two compressors. So let's say air enters the first compressor. After that, it goes to the intercooler in order to decrease its temperature. After that, it is sent to the regenerator, which is the new equipment that we have in part B. And after that, we have the combustion chamber. And after that, the working fluid or air is sent to the turbine. Reheat between them. All right, and finally sent to the regenerator. Okay, so this is the direction of the cycle. And what I'm going to do, I'm going to use the same points that I had before in the previous schematic. Let's say 1, 2, 3, 4. Okay, so before the turbine, it was 5, 6. So 6 is here, 5 is here, 7, 8. So this is 1, 2, 3, 3, 4, 5, 6, 7, 8, and I'm adding a point here and also a point here. So let's say after the regenerator, let's call it point 9, and here I can call it point 10. Okay, so this equipment that I added is my regenerator, and there is a shaft that connects all these 4 equipment to each other. You can assume the shaft is continuing and there is a rotation here. Okay, compressor 1, compressor 2, turbine 1, turbine 2. And obviously the reheat is still causing the heat addition. So there is heat addition here, there is heat addition here, there is a heat transfer here. So basically in the regenerator, what happens is the exhaust gas coming from this turbine is at a pretty high temperature, so it can warm up the air coming from the compressor before going into the combustion chamber. So this is the direction of heat transfer within the regenerator, and this is the heat addition Q in here and Q in here. Okay. All right, so the TS diagram is in fact pretty similar to the TS diagram that we had before. Temperature versus entropy. And also I have 2 high temperature values. Okay, so from 1 to 2, I still have increase in temperature. From 1 to 2, from 2 to 3, we are decreasing the temperature within the intercooler. From 3 to 4, the temperature increases. And then let me skip point 10. Let me just do the regular TS diagram that I had before. So let's say this is 4 to 5, which is before the turbine. And from 5 to 6 I have this one. From 6 to 7 I have my reheat, and from 7 to 8 I'm here. So let's say if I want to continue that, although it doesn't really happening, but let's say I can do something like that. So let's say point 9 is somewhere here. Okay, now point 10, I need to add point 10. Point 10 is definitely between 4 and 5. All right, so this is 4. This is 5, and point 10 is happening somewhere here. We don't really know where. So let's say this is my point 10. But what I would need to be able to be able to solve this problem is the enthalpy value at point 10. This is the reason. So the back work ratio is the compressor work to the turbine work. All right. The compressor work doesn't really change. Likewise, the turbine work doesn't really change because H1 and H2, H3 and H4 are the same. So because of that, the compressor work is the same. Also, H5, H6, H7 and H8 are the same. So these turbine work is exactly the same. So at the end of the day, my back work ratio doesn't really change. So it's the same value that I had in part A, and that was 0.335. The only thing that changes by having this regenerator is the thermal efficiency, okay? Because the thermal efficiency is the net work over Q in. In this equation, the net work doesn't really change compared to part A because the net work is WT minus WC, okay? So this net work is still the same as I had in part A. Same as before. But the only thing that is going to change is this Q in, okay? Because right now we are spending less fuel in order to add heat within the combustion chamber. Okay, so in order to find that Q in value, I need to have H10 because Q in here is H5 minus H10. But I don't really know the value of H10 unless I analyze this regenerator, okay? So the problem statement, if I get back to the problem statement, gives me and effectiveness for the regenerator. So it says the regenerator is 75% efficient. Okay, I'm going to use that value because effectiveness in a regenerator, so this Greek letter represents the effectiveness, that is Q regenerator to Q max. Okay, so this is the heat addition done within the regenerator, and that is from H4 to H10, or basically value wise it's going to be H10 minus H4. H10 minus H4. Okay, Q max is the maximum possible heat addition. Okay, looking at the TS diagram, Q max is going to be H8 minus H4. Okay, because the maximum this regenerator can increase the temperature is to raise the temperature equal to 0.8. That is the maximum it can do, because 0.8 is right after the turbine number 2. There is no way that the temperature at 0.10 can be greater than temperature at 0.8. There is no way it happens. All right. In fact, in real life, H10 is also never equal to H8. H10 is always less than H8. So that's why we say that H8 or T8, temperature at 0.8, is the maximum theoretical possible temperature. Okay, so this effectiveness is given. H4, I have it in the previous step. Same thing here, same thing here. So based on that, I can find H10. H10 is equal to 811 kilojoule per kilogram. All right. So for H4 and H8, I use the values that I had before. So by having this H10, I can develop heat addition equations. This time Q in is going to be 1 from 10 to 5 and 1 from 6 to 7. So Q in is H5 minus H10 plus H7 minus H6. Okay, so H7 minus H6 is the same value as I had before. So the only part that changes in Q in is this part, in fact H10. Previously, in the previous schematic, we had H5 minus H4 for Q in plus H7 minus H6, but right now we have H5 minus H10. That's the only difference. So Q in is going to be equal to 798 kilojoule per kilogram. And as I said, the back work ratio is still the same. The compressor work doesn't change. The turbine work doesn't really change. The only thing that is going to change is the thermal efficiency. So the thermal efficiency is the net work, which is same as before, 442 kilojoule per kilogram. And my Q in is 798 kilojoule per kilogram. So that gives me a thermal efficiency of 0.553, or you could say the thermal efficiency is 55.3%. Right? So if I get back to the schematic and the TS diagram, I can show the Q regenerator from 4 to 10. So from 4 to 10 is my Q regenerator. And then from 10 to 5 is my heat addition. So from 10 to 5 I have my Q in. And also from 6 to 7 is my heat addition, Q in. And the other thing is, just to review, we don't really need that in this problem, but the process from 6 to 7 is a P constant process because this is an ideal cycle. And finally, for the conclusion, I can make a conclusion that by utilizing the regenerator, the backwork pressure didn't really change, but in fact the thermal efficiency increased as we utilize the regenerator. So the regenerator did not change the backwork ratio. And the second bullet item is by utilizing the regeneration, the thermal efficiency increased from 36.8% to 55.3%. So basically, the regenerator is increasing the thermal efficiency. That is all it is doing. Thermal efficiency.